All right, let me close the door. The dog is going crazy as usual. Okie doke. So, as promised, I wanted to go through these solutions, at least verbally, with you. If you read the PDF document, it somehow or other the scanner keeps jumbling the pages. I have no idea why it's doing that, and it seemingly does it at random. So I apologize for you trying to read through this thing and have it make some sense. But we're going to do them as they come up, and it's slightly out of order, as you'll notice. All right, so but there were a few problems with this. The first one, you want to show that a set that was bounded above has a sup that belongs to its closure. And if the set is closed, then of course, then it's a max. All right, so we'll show that. We'll look through the sup one, and then the inf one is basically identical in terms of how the strategy of the proof, but you'll use upstream instead of downstream property and that sort of thing. Then number 29, actually 29, if you see it, it's easy. And if you don't, you could be there forever. So we'll look at that. Actually, yeah, no, I'm thinking of 31. 29 wasn't too bad. 31 was the one that could take you a while if you don't see it right off the bat. 30 is quick. Those are examples that we'll look at. And 32, the first part of it arguably is the hardest, and then it gets easier as you go along because none of them tend to be true because of the nature of countable and uncountable sets. But let's actually go through this and see how everything worked. All right, so this is part of, you'll see a number 30. So we'll come back to that. All right, the first one that we're going to look at is if you have a countable collection of pairwise disjoint open intervals or open sets, then it has to be countable. All right, so pairwise disjoint simply means that if you took any two of the open sets in the family, their intersection is empty. Right, so you can think broadly as the open sets being open intervals, because in the real line, if you just take the usual sort of definition of an open set for us, it turns out that the basic open sets are open intervals. And so you can prove that every open set is a countable union of open intervals, right? So you can just kind of think of spreading these things around, and how would you kind of enumerate them? All right, so let's actually take a set. We'll call the set, the family of sets G gamma, where gamma is in big gamma. And we'll assume that all the G gammas are open and that none of them overlap. That's what this condition means. What we're going to do is define a mapping from the set of open sets, so this guy, into Q by simply taking any element of the rationals that lies in G gamma, and I'm going to map the whole open set to that particular rational. Okay, so keep in mind that if it's a non-empty open set, then there are infinitely many rationals to choose from. Just choose one, doesn't matter what it is. Since the G gammas are all pairwise disjoint, you never use the same rational number in this mapping, so it has to be one-to-one. And furthermore, you're only mapping into Q, and Q is countable. So the range of F is countable, but the range is exactly the number of elements you're mapping to the set family of sets, right? And so we know that that set has to be at best countable. It fails if it's closed. Just take G gamma to be the singleton gamma, right? If you allow that, if you take this collection where gamma runs through the whole real line, certainly all singleton sets are closed. And furthermore, there are uncountably many of them, right? So you have an uncountable collection of pairwise disjoint closed sets, but that's uncountable, right? So it does not work if you replace the open sets by countable ones, or by closed ones rather. All right, this one. So let's provide some examples, right? So you want a bounded infinite set with exactly one limit point that's not in the set. So there are a lot of examples here, but the most natural way to go is this one here, right? So you can't take an open interval or any set that's dense in the real line because there are infinitely many limit points, right? So you almost have to take a single, like a sequence type set like this for what that converges, and that point to which it converges can't belong to the set to satisfy this example. So I just used the set of 1 over n, where n was a natural, and certainly that is bounded, right? Everything is between 0 and 1 inclusive. It's infinite because none of these elements overlap, they're not the same, and we know that n is infinite. And there's precisely one limit point, 0, which is not in the set, right? So that would be an example there. All right, and then you want, similarly for B, you want a bounded infinite set with one limit point in the set. We'll just clap on the singleton element to which it converges, and that would do it for that example. So the thought here was kind of knowing that you had to look at a sequence type set for this particular problem. Okay, this one. So this one is a little tricky. Give me any uncountable subset of R. All right, what you want to show is that it has to have at least one limit point. Well, the idea here is you don't know anything about where the elements in A are scattered, right? You simply know there are uncountably many of them. So technically, A could be a very tiny closed interval union with a sporadic number of points, or it could be the irrationals. I mean, the structure of such a set is, there's many different ways you can think of it. So what you have to somehow do is line up one of our theorems that enables you to argue the existence of a limit point without knowing the structure of the set, aside from some sort of underlying characteristics. All right, so what did I do? I took, give me any n that you want, any integer, and I constructed these closed intervals from n to n plus 1 along the real line. Now, I know that there are countably many such intervals because, for one, z is countable. The endpoints of these intervals are the integers, and they're abutting, right? So you have countably many of these closed intervals. And furthermore, if I intersect each one of those with A, right? So some of these intersections may very well be empty, right? But I know that at least one's not because A is uncountable, right? So in fact, I know that if I looked at the union of all those guys, right? So if I union all of these sets up by the distributive property, this union of this intersection is equal to A intersect the union of all those guys, but the union of all these intervals is R itself. And so A intersect R is equal to A, right? So in other words, I can represent the set A that I give you, the uncountable set A in R, as this union. And it's a countable union, right? Okay, so what do we know? Well, we know that since A is uncountable, and this is a countable union of sets, not all of these sets can be countable, right? Does that make sense? If not all those are countable, then one of them has to be uncountable, right? Otherwise, a countable union of countable sets is countable. Okay, so there has to be an integer for which that set's uncountable. In particular, we don't need the uncountability of it. We just need the fact that the intersection's infinite. Now, why? Well, if the intersection of A with this set is infinite, we already know it's bounded because you're intersecting two sets, one of which is bounded, right? The intersection of these guys is a subset of this closed interval. And so for this particular n naught, this set is bounded and infinite. We know by Bolzano-Weierstrass that that has to have at least one limit point, right? And so there has to be a limit point of that set. That limit point does not need to belong to this set, but it does have to belong to the union and hence into A. All right, and so that's how you would argue that particular one. Hold on one second, let me let the dog out again, sorry. Benjamin, here, behave yourself. Okay, let's go on to the next one. Actually, I'm going to cut forward to, let's actually go to this one. This was the first one on the list. All right, so here we said that if A was a set that was bounded above, it had to have a sup that belonged to its closure. All right, and so let's look at that. Let's let A be a non-empty set bounded above. By completeness, we know there has to exist a sup, right? That's what completeness of R tells us. But now, can you close that door, please? But now by the downstream property, okay, sorry about that. Okay, so we have a sup. Now what we have to argue is that the sup belongs to the closure of A, right? What does that mean? It means that no matter what interval you give me around this element, the intersection with the set A has to be non-empty. Well, we know that has to be the case by the downstream property, right? For any epsilon, go downstream by epsilon, this half open, half closed interval has to hit A, right? And so if that's true, then sup of A belongs to the closure of A, just from the definition. Now, if A happens to be closed, then A is equal to A bar. That's what definition of closure is. And so if that's true, the sup of A belongs to A, but if the sup belongs to the set of which it is a sup, it's the max. And so the max has to exist. All right, so that's all you really have to do with that one, is make use of that property. All right, so a lot is embedded in the completeness of the real line that makes this work. All right, and then I don't even write the solution out here. For the inf of A, you simply go upstream from the inf, and then you argue the same way. Okay, for the last problem, the compactness problem. So here you had a set, let's actually recall what the set was. So you have a set A that's defined to be this union. So you have two sequence sets and a set containing two elements that just so happen to be the numbers to which these sequences converge. So 2 is a limit point of A, 5 is a limit point of B. And what you want to argue first, using the definition of compactness, that's the open cover definition, you want to prove that's compact. And I gave you a hint to mimic the example that I gave you in the PDF. That one only contained one sequence set, right? So now you're just kind of taking two of them together to argue that. And then what we do is we adjoin a finite set in both union and intersection and ask if those have to be compact. Then we assume the set B is countable and ask the same question. And then finally, if it's uncountable, we'll ask even the same question again. Right? So we're doing the same thing, but we're seeing if the cardinality of the set that we're adjoining on in either of these ways has an impact. All right, so let's go back down to the solution. All right, so let's take an open cover of A. Let's call it G gamma for gamma and gamma. We have no idea of what those open sets are. We simply know that A is a subset of the union of all those G gammas. That's what it means to be an open cover. What we have to argue is that that open cover has a finite subcover. And what that means is you should be able to pluck out finitely many of those sets and in such a way that A is a union of those finitely many sets. That's what it means to be a finite subcover. All right, so what you want to do is you want to cover the infinite parts of A in as few sets as possible, leaving only finitely many out. That's the idea. And so here we know that the observation was that 2 and 5 were the limit points of interest. And so since they belong to the set A, we know there have to be two indices. We'll call them gamma 0 and gamma 0 star. They could be the same one, who knows? But there have to be indices for which 2 belongs to G sub that index and 5 belongs to G sub that index. Have no choice because they belong to A and these sets cover A. But remember, the G's are open. And so this should be a G gamma 0 star here. But since these two sets are open, we know there have to be epsilon 1 and epsilon 2 positive for which these entire intervals are a subset of G gamma 0 and G gamma 0 star. And the reason for that is that if these are open sets, then every point is interior. And so 2 is an interior point of G gamma 0, and 5 is an interior point of G gamma 0 star. All right, so what we have is an entire interval centered at 2 inside that guy, and an entire interval centered at 5 entirely inside this guy. But let's think about how these sequences work, right? We know that I can find integers, and this is basically using the Archimedean property without showing all the detail. But we can prove that these guys here get sufficiently close to 2. And so what does that mean? Well, if I choose n big enough, then all of the elements of the set of this form will be in this interval past that big enough n. So I'm going to call that n1. Let's say it was 1,000 for definiteness. Then what I mean here is that if I put any n larger than 1,000 in here, this number will be sufficiently close to 2 as to be inside this interval. Okay. I don't know what this n1 is, aside from the fact that it has to depend on the epsilon 1. Right? We'll talk more about that in the next chapter on sequences. But think of it this way: the smaller the epsilon 1 is, the bigger the n1 has to be to accommodate the smaller target around 2 to get into. All right, so there have to be these indices for which this is true each time, right? And so what we've gotten is all but finitely many members of that first sequence set inside of G gamma 0, and all but finitely many of the second set of that union inside of G gamma 0 star, leaving finitely many outside each time. Well, that's fine, because you can cover each and every one of these elements by its own G gamma, right? So they might all be contained in the same one, I don't know. But what I do know is that each of these guys has to belong to some G gamma. And so let's just think of it as the worst case and take for every one of these n's in each one of these guys, take a new G gamma, let's say, they'll label it differently. And so you have still finitely many open sets here that cover this particular part of the set. But look at what we've done. We have the infinite portions, all but finitely many elements of the set A are in these two members of that original open cover. Then we have finitely many other sets that cover the rest. And so what we produce is a finite subcover of the original cover. And so the set A is compact. Okay, so that's how you want to think of that. Okay, now if B is finite, all right, if you union A in a finite set, is it still compact? Well, yes, and you can use the same argument here to work that. Take any open cover of A union B, use exactly the same process we did above to cover A with finitely many of those sets, and then there are only finitely many more to cover B. So just at worst case, just choose another, whatever the cardinality of B is, choose that many distinct G gammas from the original cover, they have to cover B. And so if you union those on with the original subcover that we have in the first part, that would be a finite subcover of A union B. All right. And then the intersection is even easier, because A intersect B has to be a subset of B, right? If it's a subset of B, yeah, and it itself is finite, and all finite sets are compact, right? You can prove that easily. Just take any open cover of a finite set. You can just take one element per open set and map them that way. So if your open set contained P elements, use P of those open sets, even though there might be uncountably many of them. All you need are P of those open sets, each one that contains each of those elements, and that automatically produces a finite subcover, right? So this would be true as well. All right, so now let's increase the cardinality a bit. If B is countable, must A union a countable set be compact? And the answer here is no. And the most extreme example I can give you is using the rationals, right? If I union A union B, A was comprised of nothing but rational numbers. And so in fact, A is a subset of B. So A union B is the rationals itself. And we know that's not compact, right? They spread through the whole real line. So there's easy to produce an open cover that does not have a finite subcover. And the intersection, must the intersection of A and B be compact? And the answer, this one's trickier. The answer here is no. And what we're going to do is we're going to take B to be everything in A except for its limit points. Okay? So if you do that, it's countable because A consists of the two sequence sets, right? And so both of those guys were countable, in fact, enumerable, nothing overlapped. But the intersection of A intersect or A of A and B is B, right? Because B is a subset of A. And so if you look at this set here, that set's not compact because you can construct an open cover so that each of those open sets contain exactly one element each time. There's no way to guarantee that you get the whole tail of one of those sets in a single G gamma because there's no limit point inside the set to capture it, right? And so you can construct in this case a decreasing sequence of open intervals that march to 2 and also that march to 5 in such a way that each open interval contains a single element of this set. Right? If that's the case, you'll never be able to extract a finite subcover because each and every element of that open family has to be in a cover. Right? Because if you remove that particular one to get a reduced cover, that one element's not going to be covered by the remaining sets. And so in general, if you intersect a compact set with a countable one, a denumerable one in particular, the result need not be compact. Okay, and then what's your guess for the others? The minute these fail for countable, they fail in a more miserable way for uncountable, right? Just take B to be open 0, 1. If I union A with B in this case, then certainly you get all of open 0, 1 plus more elements. That's not a compact set at all, right? You can take an open cover of those guys in such a way to actually not be able to extract a finite subcover. Okay. And for intersection, no as well, but build on the last example, right? We're going to take A, throw away its limit points, whereas I want to guarantee that I can't be able to handle the finite portions of those sets with a single open set in the cover. But I'm going to clap on then an uncountable set to this. The minute that happens, A intersect B union that uncountable set is still this part, and that's not compact. All right, and so that's how you argue those. So if this one didn't go well, maybe just sit back and process kind of the strategy again, just to kind of see the approach to try to get comfortable with that. All right, and I think that is it for these. Okay. The next part that you're working on is the remainder of the topology section. So you're going to see various theorems about closed subsets of compact sets are compact, closed intersect compact is compact, and then you're going to get to a lemma that proves that closed and bounded intervals of, like, say, close A to close or close A to close B is a compact set. That lemma is where all the heavy lifting is for the theorem called Heine-Borel. And what Heine-Borel says is that a set in R is compact if and only if it's closed and bounded. So this is a R-specific result, right? It does work for other complete metric spaces, but not, I mean, they have to be Euclidean in nature for it to work in general. All right, so that's kind of what you're working on next. And then you'll have an introduction to sequences, which just gives you a notion of what a sequence is and kind of lightly introduces the notion of increasing and decreasing and whatnot for sequences. Okay, so review these. Let me know if you have any issues. And if not, then I'll see you next Wednesday. Okay, bye.